Okay, so in this video we're going to go ahead and review the central limit theorem. The focus is to try to understand the theorem and do some simple calculations. Okay, so the first version of the theorem is for normally distributed populations. So it says the following: let x be a random variable which is normally distributed with a mean mu and a standard deviation sigma. Then the sampling distribution of sample means x bar from all samples of size n will be normally distributed with a mean of mu and a standard deviation of sigma divided by the square root of n. Okay, so to understand this theorem here, let's make sure we understand the assumptions. So here we have a random variable x. In other words, we have a population of x data values that are normally distributed. So the population, x is the population data, right? And we're saying that it's normally distributed, which means it takes on, the shape, if you did collected data, you would get a shape that looks like a mountain shape, a mountain symmetrical shape. Okay, so if you did a histogram, for instance, you might get that shape. We know that the peak always falls under the peak there. The mean falls always under the peak there. And basically, the standard deviation is telling you how wide or narrow this curve will look like. And so just to remind you, mu is the population mean of the x data, and sigma is the population standard deviation of x. Okay, so that's the assumption, and basically what we're doing is looking at a sample. The central limit theorem is that we're looking at the sampling distribution of sample means, and the result basically tells us how the shape of the sampling distribution means look like, the middle of the sampling distribution, or the center, and it also tells you how it varies, or how much spread there is in the sampling distribution of means. And so the results are the following. Once again, reminder, we are picking a sample of size, a sample of a certain size. Okay, and the results is that x bar, which is the sampling distribution of means, is normally distributed. So it's telling us the shape of the sampling distribution of means. So once again, when we say normally distributed, it means that the shape of this looks something like that. Let me draw that a little bit better. And once again, the peak is under the peak. The mean of the sampling distribution means will be under the peak there, and we denote that as mu sub x bar, and how wide that is there is sigma of x bar. Okay. Once again, mu sub x bar is just the mean of the sampling distribution of means. Sometimes we just say the mean of means. Likewise, sigma of x bar is the standard deviation of sampling of the sampling distribution. Of the sampling distribution, and I can't spell, sampling distribution of means. This is sometimes also referred to as the standard error. I'm just going to copy that there. Okay, and so that is the result. So once again, it's telling us the shape of the sampling distribution of means. when we know that we're looking at samples from a population that is normally distributed. All right, well, this theorem has a little bit more of a general version of it, which kind of basically has the same results, and the assumptions or the conditions that one needs to meet is a little bit more relaxed than the one above. So this is what we usually typically is referred to as the central limit theorem. So if the X distribution has any distribution, so that's one big change there, is that it has any distribution, and suppose it has a mean of mu and a standard deviation of sigma, then the sampling distribution X bar based on random samples of size n sufficiently large, and for us we'll take that to mean n greater than or equal to 30. We'll have a distribution that is approximately normal with a mean of means equal to mu and the standard deviation or the standard error equal to the population standard deviation divided by the square root of n. Okay, so once again, the X population, the assumption is that there's no really any assumption on X. We're saying that it has any distribution. So the X population can be from whatever population. So just to remind you of some few populations of it that we've encountered, you might have a population of data that is uniformly distributed, right? Uniformly. Maybe even something that's not uniform, but more, say, bimodal, for instance. Or maybe not even a population that is coming from continuous type of data, but maybe it's more of a discrete type of data where the distribution maybe looks something like this. And I'm using a dot plot here to kind of illustrate that. Okay, like I said, any type of distribution. There's no assumption there. Okay, and so all the thing here is that so there's no assumption on the X population data. However, we assume the population that the samples that we're pulling from the population are large enough, sufficiently large. And so for us, that means we'll assume about n greater than or equal to 30. However, sometimes the sample sizes need to be bigger depending on the distribution. Okay, and so if we meet that condition, then basically we get the same results from earlier, that we know the shape of the sampling distribution of means is going to be normally distributed. In other words, it has this bow shape, and the mean of means is going to equal to the population mean, and the standard deviation of sampling distribution of means is going to equal the population standard deviation of X divided by the square root of n. I probably forgot to write that down above, so once again, it says it in the theorem that the mean of means is equal to the mean of X, and the standard deviation of the sample mean is equal to the population standard deviation of X divided by the square root of n, where n is the sample size. In other words, if we're looking at a sampling distribution of samples of size, say 40, then n will equal 40. All right, let's look at some examples. Match the following three histograms to the distribution of the population. Match the following three histograms to the distribution of the population, distribution of a single sample, and the sampling distribution. All right, so we have three scenarios here. We have the shape or the shape of the population. Then we basically sample from that population. So then you have what's called the sample distribution, and you have essentially the shape of the sampling distribution of means. In this case, we'll think means. Okay, so once again, by the central limit theorem, we know that we have some population, and this here appears to be the shape of the population. Okay, and if we sampled from this population, like we went out and gathered a sample size 40 from this population randomly, then the sample should look somewhat like the population. a little miniature version, especially if we're doing it randomly. Okay, and so that means probably C looks closely related to B, to the histogram of B, so that would be the shape of the sample distribution. Okay, and then of course the central limit theorem says if you're looking at the sampling distribution of say means, for instance, then the shape should have a mound shape. Okay, in other words, it should look normal, and so this would be the sampling. This would be the shape of the sampling distribution, and in our case here of means, and that's how it should look. Okay, so that's that example. Let's move on. Next example here. The number of units taken by college students is approximately normally distributed with a mean of 15 units and a standard deviation of 1.6 units. All right, so we're asked to write the correct notation for the probability that a college student selected at random is taken between 14 and 16 units. So first let's think about the random variable. So what is the random variable here? X would be the random variable, and it's essentially the number of units taken by a college student. And based on this, we're told that it's approximately normally distributed with a mean of 15 units and a standard deviation of 1.6 units. So that's essentially telling us that the mean of the X is 15 and sigma is 1.6. So we're not actually doing any calculation here except represent the probability that we're looking for here. So we use a capital P to represent probability, enclose the event in parentheses. So the probability of my event X falling between 14 and 16 units would look like something like that. Maybe not necessarily with the units written there. Okay, and so that's how we would represent the probability that our random variable X falls between 14 and 16. Next example here, if a random sample of 11 college students are selected, write the correct notation for the probability that the mean number of units taken is between 17 and 19. So no longer are we talking about the random variable X, but rather the random variable of sample means. In other words, we're looking at the sampling distribution of means. So this is the mean number of units taken by a sample of 11 college students. And the way we denote that there is probability P falls between 17 and 19. So we would say probability that my sample mean is between 17 and 19. And we could express that using a double inequality there, right? So the probability that the mean number of units is between 17 and 19 can be represented like that. So in practice, you're actually finding these values. And just remember, the way you would calculate the one above and the one below would be a lot different. It would be slightly different because here the mean of means would equal the mean, but the mean standard deviation of the means would be the population standard deviation divided by the square root of n. So in this case, we would have 1.6 divided by the square root of 11. And the population mean of X and the mean of means would be exactly identical. And so when you do the calculation practice, you got to remember this is very important. And that's the difference between the two calculations. All right, next example. The size of fish is very important to commercial fishing. Suppose the length of Atlantic cod caught in nets has a mean of 49 centimeters and a standard deviation of 3.5 centimeters. Assume that the length of these fish is normally distributed. Okay, so X here is the length of Atlantic cod. Okay, and we're told that the mean is 49 centimeters, and the standard deviation is 3.57, and we're told x is normally distributed. And that's the shorthand notation to express that. We're asked to find the find the center and standard error of the sample distribution of means. So this is talking about x bar, where x is the mean length of Atlantic cod. So it's the mean length of Atlantic cod for samples size 38. In other words, we're told that we're looking at samples of size 38. So the sample and distributed means of samples of size 38. While by the central limit theorem, we know can be applied here, which means x bar is going to be normally distributed. And it's going to have the mean of means equal to the mean or the population mean of the length of Atlantic cod. So we know that's 49 centimeters. All right, but the standard error or the standard deviation of the sampling means sigma of x bar sub x bar is equal to the population standard deviation of Atlantic cod, right? Lengths of Atlantic cod divided by the square root of the sample size. Okay, so we know sigma is equal to 3.57 centimeters, and we divide that by the square root of the sample size. In this case, we're looking at samples of size 38. Okay, so we take that number 3.57 and divide by the square root of 38 if we wanted a decimal approximation. Let me do that now. So this is roughly, and this is going to round to maybe 4 decimal places, 0.5791. Okay, so we're asked to complete this statement rounding to the nearest tenth of a centimeter. Okay. All right, so about 99.7% of the time, the mean length of a sample 38 fish will be between blank centimeters and blank centimeters. Okay, so we could use the empirical rule to give us an idea here, because we know x bar has a sampling distribution. And so this picture here that you see is the empirical rule. And let me go ahead and insert a picture, a very similar picture. Okay, and so we know that what we're looking for is 99.7%. So if you look at the empirical rule, the lengths in this case has to fall between the mean minus 3 standard deviations and the mean plus 3 standard deviations. So we need to do that calculation. So we know the mean is 49 centimeters. So that's right under the peak. And then I'm going to go ahead and number up by 3 standard deviations and number down. So I'm going to use my 0.5791. It's probably better to take more decimal places, but just for an emphasis here, I'm going to go ahead and figure out what that would be if I add 1 standard deviation to the mean using 0.5791. And if I do that, I would get 49.5791. If I do it again, I would get 50. Actually, it said round to the nearest 10. So let me back up here. Let's round this to the nearest 10th. So that would be 0.6. So this would be 49.6. My apologies. And let's do that again. 49.6 plus 0.6 gives me about 50.2. And then let's do it again. We get 50.8. Okay, so now that's going up by standard deviation. Let's go down by standard deviations. 1 standard deviation, 2 standard deviation, and 3 standard deviations. So we have 49 minus 0.6, so we get 48.4. Let's do that again. Subtract 0.6, we get 47.8. Let's do that again. So we get 47.2. Okay, so we know that the 42.2 and the 50.8 are 3 standard deviations below and above the mean. And so we know by the empirical rule that all our values between there and there, we would expect about 99.7%. Okay, so then how to complete the statement? Well, about 99.7% of the time, the mean length of a sample of 38 fish will be between 47.2 centimeters and 50.8 centimeters. All right, let's look at the next part. Suppose you catch a sample of 38 fish and find its mean is 49, and I believe I left off centimeters. Should that sample be considered unusual? Okay, and here we're going to take the word unusual to mean and I'll say an unusual measurement or observation. Observation falls beyond 2 standard deviations. Of the mean. And here we're looking at the X bar distribution, so we're using the information from part B here. And so we have a measurement of 49 centimeters. 49 centimeters would be actually at the mean. I'm not too sure if I left something off there, but in any case, we see that 49 centimeters falls within 2 standard deviations of the mean, which once again, let's do that in red there. That would be 2 standard deviations of the mean. Okay, and so if you're beyond, like over here on the left of that or to the right of that, then that's what we would call unusual territory. And so in this case, no, the sample is not unusual. Okay, but however, if it were like, say, I don't know, 1 centimeters, if we had then an observation like that would be unusual. Therefore, the sample would be unusual because it's falling beyond the 50.2, which is 2 standard deviations above. Okay, so that's it for this video.